Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 777, swap adjacent in LR string. This is an interesting string manipulation problem that tests your understanding of character transformations while maintaining specific constraints. Let's dive in and explore how we can approach this problem step by step. In this problem, you are tasked with determining if it is possible to transform one string, called start, into another string, called target, by following specific transformation rules. Both strings are of the same length and consist of the characters L, R, and X. The transformation involves swapping adjacent characters, but with restrictions. Specifically, L can only move left by swapping with X, while R can only move right by swapping with X. The character X acts as a placeholder to facilitate these movements. The goal is to return true if the transformation is possible, and false otherwise. The input consists of two strings, start and target, and your output will be a Boolean value indicating whether the transformation can be achieved under these rules. To clarify the problem, let's look at an example. Here, start is given as RxXLRXRXL, and target is XRLXXRRLX. The output for this case is true. The transformation is achieved in several steps. First, the R at position 0 and start moves to position 1, resulting in the string XRXLRXRXL. Next, the L at position 3 moves left to position 2, giving us XRLXRXRXL. These movements align with the rules, as R moves to the right and L moves to the left, facilitated by the X characters acting as placeholders. Continuing from there, the transformation continues with the R at position 5 moving to position 6, resulting in XRLXXRRXL. Finally, the L at position 7 moves left to position 6, giving us XRLXXRRLX. At this point, the start string matches the target string, so the transformation is indeed possible, and the output is true. This example demonstrates how the rules allow specific movements that eventually align the two strings. Now consider another example where start is X and target is L. In this case, the output is false. Here, the target string contains no X, which makes it impossible to rearrange the characters in start to match target. This violates the rules, so the transformation cannot be achieved. Additionally, another example is provided where start is LLR and target is RLL. The output here is also false. The issue is that the relative ordering of L and R in start and target is incompatible with the movement rules. Since R can only move right and L can only move left, their positions cannot be swapped to match the target string. Finally, let's review the constraints for this problem. The lengths of both start and target are guaranteed to be the same, with values ranging from 1 to 10 to the power of 4. Both strings consist only of the characters L, R, and X, and the count of each character is identical in both strings. Importantly, the movement rules must be followed. L can only move to the left, and R can only move to the right, using X as a placeholder. Furthermore, the transformation must preserve the relative order of L and R in both strings. These constraints ensure that the problem is well defined and solvable within the given rules. To solve problem number 777, the goal is to determine if we can transform the string start into target by repeatedly swapping adjacent L and X or R and X, while following specific movement constraints. Here's what those constraints mean: L can only move to the left, and R can only move to the right. One possible way to approach this is through a brute force method. The intuition behind this approach is to simulate all valid transformations of the start string by applying swaps where L moves left and R moves right. We then check if the target string can be reached through any sequence of these swaps. To implement this, we could use recursion or backtracking to explore all the possible valid states. However, the drawback is that this method is computationally expensive. The time complexity grows exponentially, meaning it becomes infeasible as the length of the strings increases. Additionally, the space complexity is high because of the storage needed for intermediate states and the recursion stack. This makes the brute force approach impractical for larger inputs. Now, moving on to a more efficient solution, we can use an optimized approach that leverages key observations about the problem constraints. Instead of simulating every possible transformation, we focus on the movements of L and R. The first key observation is that the start and target strings must have the same number of L and R, in the same order, when ignoring X. Secondly, L in start cannot appear to the right of its corresponding L in target because it can only move left, and similarly, R in start cannot appear to the left of its corresponding R in target because it can only move right. With these constraints in mind, we can use a two-pointer technique to compare the positions of L and R in the two strings. The implementation involves two main steps. First, removing all X from both strings and checking if their sequences of L and R match. Second, using two pointers to verify that the positions of L and R satisfy their movement constraints. This approach is highly efficient with a time complexity of O(n) and a space complexity of O(1), making it well suited for larger inputs. By focusing only on the essential constraints, we avoid the inefficiencies of the brute force solution. The strategy we've chosen is the optimized two-pointer approach because of its balance between simplicity and efficiency. While the brute force approach explores all possible transformations, it is computationally prohibitive for larger inputs due to its exponential complexity. In contrast, the optimized approach directly addresses the problem by leveraging the insight that the relative order of L and R, ignoring X, must remain the same, and that their positions must adhere to movement constraints. This realization eliminates the need for unnecessary computations, allowing us to solve the problem in linear time. However, the optimized approach does require careful implementation to ensure the two-pointer logic is applied correctly, avoiding errors in edge cases. Overall, this method offers the best trade-off between clarity, correctness, and performance, making it the most practical solution for this problem. This problem challenges us to determine if we can transform the string start into the string target by following strict movement rules for the characters L, R, and X. Here, L can only move to the left by swapping with X, while R can only move to the right by swapping with X. The X character acts as an empty space that facilitates these swaps. To solve the problem efficiently, we begin by checking the basic validity of the transformation. First, we remove all X characters from both strings. If the sequences of L and R in the resulting strings are not identical, the transformation is immediately deemed impossible, and we return false. This ensures that both strings have the same fundamental arrangement of L and R. Next, we compare the positions of L and R in both strings. For every L in the start string, the corresponding L in target must be in the same position or further to the left. This ensures that L only moves leftward during the transformation process. Similarly, for every R in the start string, the corresponding R in the target string must be in the same position or further to the right, ensuring that R only moves rightward. We then handle edge cases to ensure robustness. For instance, the number of L and R must match exactly between the two strings. If one string has more of either character, the transformation is impossible. Additionally, we account for cases where the strings contain only X characters. In this scenario, any arrangement is valid as no movement constraints apply. We also confirm that no L crosses an R during the transformation, as this would violate the movement rules. The key insight here is that the constraints on L and R govern the transformation process, making it unnecessary to simulate the actual swaps. By focusing solely on the positions of L and R, we simplify the problem significantly. The X characters serve as placeholders, enabling L and R to move but without altering their relative order, which is central to solving the problem. By removing the X characters and concentrating solely on L and R, we reduce the problem to a straightforward positional validation. This eliminates the need to simulate every possible swap, saving computational resources. The primary data structures we use include two pointers to traverse both strings simultaneously and temporary filtered strings that exclude X. These filtered strings allow us to quickly verify if the sequences of L and R are identical, which is the first step in our solution. Now, let's walk through the algorithm implementation. First, we check if the lengths of the two strings are unequal. If they are, we return false immediately because a valid transformation requires strings of the same length. Next, we create filtered versions of the strings by removing all X characters. If the filtered strings are not identical, we return false. This ensures that both strings contain the same sequence of L and R. We then use two pointers to traverse the original strings, skipping over X characters in both start and target. As the pointers traverse the strings, we check if the current characters in both strings match. If they don't, we return false because the transformation is invalid. For characters that do match, we enforce their movement constraints. If the character is L, its position in start must be greater than or equal to its position in target, ensuring that L only moves left. Conversely, if the character is R, its position in start must be less than or equal to its position in target, ensuring that R only moves right. If either constraint is violated, we return false. Finally, we move both pointers to the next character and continue the process. If both pointers successfully traverse their respective strings without encountering any violations, the transformation is valid, and we return true. By adhering to these steps, we solve the problem efficiently without simulating the actual swaps, leveraging the constraints on L and R to guide our implementation. To solidify our understanding, let's examine a few edge case examples. In the first example, where start is RXXLRXRXL and target is XRLXXRRLX, the transformation is valid. Here, R moves to the right and L moves to the left, adhering to the movement rules. In the second example, with start as XXRXXLXXXX and target as XXXXRXXLXX, the transformation is also valid. The extra X characters don't interfere with the constraints, allowing the R and L to move appropriately. However, in the third example, where start is RXL and target is LXR, the transformation is invalid because R cannot move left and L cannot move right. For complexity, the time complexity is O, n, because we perform a single pass to filter X and another pass to validate positions. The space complexity is also O, n, due to the temporary filtered strings. This combination of efficient traversal and minimal memory usage makes the solution highly optimal for this problem. Here, we define the can_transform method, which takes two strings, start and target, as input. The first thing we check is whether the lengths of these two strings are the same. If they differ, it's immediately clear that the transformation is impossible, so we return false. Next, we remove all the X characters from both strings and compare the remaining sequences. If they don't match, we return false because the order of L and R characters must be consistent between start and target. Now, we move on to assessing the positions of the L characters. We initialize two pointers, I and J, to iterate through the start and target strings respectively. While iterating, we skip over any X characters by incrementing the pointers until a non-X character is found. If both pointers remain within the bounds of their respective strings, we then compare the characters they point to. If the characters at these positions are different, we return false because it means the transformation cannot align the characters properly. Finally, we begin handling the constraints specific to L and R. For example, if we encounter an L, we need to ensure that it does not move to the right in the target string. If the current character is L, we verify that its position in the start string is not less than its position in the target string. If I less than J, it means the L has moved to the right, which is invalid, so we return false. Similarly, if the character is R, we check that it does not move to the left, which would occur if I greater than J. If this condition is violated, we return false as well. After validating these constraints, we increment both pointers to continue checking the next characters in the strings. Once we've finished iterating through the strings, we need to ensure that there are no leftover non-X characters remaining. This is done by skipping over any trailing X characters at the ends of start and target. If either pointer still points to a non-X character, it means there's a mismatch, and we return false. Finally, if both pointers have reached the end of their respective strings, we return true, indicating that the transformation is valid. Here, we begin by defining the can_transform method, which takes two strings, start and target, as input parameters. The first thing we check is whether the lengths of these two strings are different. If they are, it's impossible to transform one into the other, so we immediately return false. Next, we remove all the X characters from both strings and compare the remaining sequences. If these sequences aren't identical, we know the transformation isn't possible and return false. Now, we move to the main part of the algorithm, where we check the relative positions of the L and R characters in both strings. To do this, we initialize two pointers, I for the start string and J for the target string. These pointers will help us iterate through each string while skipping over the X characters. When we encounter a valid character in both strings, we start comparing their positions. If the characters at the current positions of I and J are not the same, we immediately return false, as the transformation would be invalid. Now, let's handle the movement constraints for the L and R characters. If the current character is L, it can only move to the left, which means its position in the start string must be greater than or equal to its position in the target string. If that's not the case, we return false. Similarly, if the character is R, it can only move to the right, so its position in the start string must be less than or equal to its position in the target string. If this condition is violated, we also return false. After validating these constraints, we increment both I and j to continue checking the next characters in the strings. Finally, we ensure that there are no remaining non-x characters left in either of the strings after the main loop ends. To do this, we skip any trailing x characters in both start and target by advancing the pointers. Once we've handled this cleanup, we check if both pointers have reached the end of their respective strings. If they have, we return true, indicating that the transformation is valid. Otherwise, we return false as there are leftover characters, meaning the transformation is incomplete. This concludes the implementation of the can_transform method. To start understanding the solution, let's analyze example 1 where the input strings are start equals rxxlrxrxl and target equals xrlxxrrlx. First, we perform some initial checks. The length of both strings is the same, which is 9. Next, we remove all x characters from both strings. This leaves us with RLRRL for both start and target, and since these are identical, we can proceed to the next step. Now, we initialize two pointers, I and j, both starting at 0. These pointers will help us traverse through the start and target strings respectively. The goal is to compare the non-x characters while skipping over the x's in both strings. For the first character, we see that start 0 is r, but target 0 is x. Since these don't match, we increment j to skip over the x in target. Now start 0 is r and target 1 is also r, so they match. We then verify the movement constraint for r. Specifically, r in start at index 0 should not move to the left, meaning I must be less than or equal to j. Here, I equals 0 and j equals 1, which satisfies the condition. So, we increment both I and j to continue processing the next characters. As we continue iterating, we encounter some x characters in the start string. At start 1, the character is x, so we simply increment I to 2. Similarly, start 2 is also x, so we increment I to 3. At this point, we find that start 3 is L and target 2 is also L, so the characters match. Now, we need to verify the movement constraint for L. The rule is that L in start should not move to the right, meaning I must be greater than or equal to j. Here, I equals 3 and j equals 2, which satisfies the condition. After confirming this, we increment both I and j to process the remaining characters. Following this pattern, we evaluate all subsequent characters by skipping over x's and ensuring that the movement constraints for r and L are met. Finally, both pointers I and j reach the end of their respective strings, confirming that all transformations are valid. Therefore, the output for this example is true. Now, let's analyze example 2, where the input strings are start equals xrlx and target equals lxxr. We begin with the same initial checks. The lengths of both strings match, which is 4. Next, we remove all x characters from both strings. This gives RL4 start and LR4 target. Here, we immediately notice that the resulting strings are different. Since the sequences of non-x characters don't match, there's no way to transform start into target, regardless of the movement rules. Thus, we can return false immediately without further iteration. This demonstrates that mismatched sequences of R and L characters make the transformation invalid right away. Finally, let's consider an edge case where both strings consist entirely of x characters. For start equals XXX and target equals XXX, the initial checks confirm that the lengths of both strings are the same, which is 3. When we remove all x characters, both strings become empty. Since the resulting strings are identical, we can proceed to character iteration. However, in this case, there are no R or L characters to evaluate, so both pointers I and j simply skip over all the x characters. As a result, both pointers reach the end of their respective strings without encountering any issues. This confirms that the transformation is valid, and the output for this case is true. In analyzing the time complexity of this solution, we can break it down into a few key steps. First, the length check, which simply compares the lengths of the start and target strings, is an O(1) operation because it involves a single lookup and comparison. Next, we remove all X characters from both strings using the replace method. Since this operation traverses the entire string once to remove characters, it has a time complexity of O(n), where n is the length of the strings. Following this, the comparison of the resulting strings involves a character-by-character check, which is also O(n). Finally, we have the two-pointer iteration, which processes both strings simultaneously. Each character is visited exactly once as we skip over X characters and validate positions of L and R. Since each operation inside the loop is constant time, the total cost remains O(n) for this step. Now, let's consider the trailing X check. This involves two while loops that iterate through any leftover X characters in both strings. These loops also traverse each remaining character exactly once, contributing an additional O(n) to the total time complexity. When we combine all these steps, the dominant operation is the traversal of the strings, which is O(n). Therefore, the overall time complexity of the solution is O(n). Looking at the space complexity, the algorithm operates directly on the input strings without creating additional copies. While operations like replace generate new strings, the memory usage is proportional to the input size, making it O(n). Additionally, the use of pointers and other variables requires only a constant amount of memory, contributing O(1) to the space complexity. Additionally, the replace operation creates two intermediate strings that exclude X characters from start and target. Since these strings are derived directly from the input, the total space required for them is O(n). When we combine these factors, the space complexity is dominated by these intermediate strings, resulting in an overall space complexity of O(n). To provide some context, a brute force approach to solving this problem would involve generating all possible transformations of the start string by simulating every valid swap of L and R. This would result in an exponential time complexity of O(2 to the power of k, where k is the number of L and R characters, as well as exponential space complexity to store intermediate states. Clearly, this would be highly inefficient compared to our current approach. The optimized solution avoids generating intermediate states entirely and simulates the transformation in linear time using the two-pointer strategy. This reduces both time and space complexity to O(n), making it far more efficient. Let's break this down further with case analysis. In the best case, if start and target are identical, the algorithm concludes after the initial checks, taking only O(n) time. For the average case, with strings of arbitrary structure, the dominant step remains the traversal of the strings, so the time complexity stays O(n). Even in the worst case, where the strings contain no X characters and are filled entirely with L and R, the solution still processes all characters in O(n) time. Mathematically, the algorithm involves a fixed number of traversals of the input strings, each taking O(n). Since there are no nested loops or recursive calls, the time complexity grows linearly with the input size. Furthermore, the space usage is proportional to the input due to intermediate string creation, confirming an O(n) space complexity. This demonstrates that the current solution is both time and space optimal for this problem. When working on this problem, there are a few common mistakes to be aware of. First, it's important to understand that L and R cannot move freely within the string. L is restricted to moving left, and R can only move right. If these movement constraints are ignored, it will result in an invalid transformation. Another mistake is failing to check that the counts of L, R, and X match between the start and target strings. Any mismatch in these counts automatically makes the transformation impossible, as characters cannot be added or removed. Finally, the relative positions of L and R must be preserved. For example, an R in the start string cannot end up to the left of where it began in the target string. Violating these rules breaks the problem's movement constraints and invalidates the solution. Another frequent oversight is not properly accounting for the role of X. While it may seem like a placeholder, X is critical because it allows L and R to move. Ignoring its positioning can lead to invalid swaps and incorrect results. Inefficient iteration is another pitfall to avoid. Some may use nested loops to check transformations character by character. However, this approach leads to a time complexity of O(n², which is not scalable for large strings. Instead, there are more efficient ways to validate transformations, which we'll explore further. When tackling this problem in an interview, focus on the movement constraints of L and R, as these are the core of the challenge. Recognizing these constraints early will help you frame your solution effectively. This problem also tests your ability to manage string manipulations under specific rules, a skill that appears in many similar problems. To optimize your approach, instead of simulating every possible swap, concentrate on the positions of L and R in the start and target strings. By comparing their indices directly, you can quickly validate whether the transformation is possible. Additionally, prepare for key edge cases, such as when the start and target strings are identical, when one or both strings lack L or R, or when the strings differ in length, which should immediately return false. This problem shares similarities with several other LeetCode problems that involve constraints or transformations. For example, LeetCode 846, Hand of Straights, requires reordering elements under specific rules. LeetCode 927, 3 equal parts, involves partitioning strings with certain properties, while LeetCode 791, Custom Sort String, tests for custom ordering and mapping, akin to the movement constraints here. LeetCode 880, Decoded String and Index, deals with transformation and indexing logic. When approaching this problem, you can use a two-pointer technique to compare start and target directly. This method is efficient with O(n) complexity but requires careful handling of edge cases. Alternatively, you could simulate swaps directly, which is more intuitive but slower, with O(n)² complexity due to repeated operations. Another effective method is index matching. This approach involves extracting the indices of L and R from both the start and target strings and comparing them to ensure their order and positions are valid. This method is both fast and clean, with a time complexity of O(n), although it does require additional space to store the indices. Each of these approaches has its trade-offs, so choose the one that best aligns with the constraints and requirements of the problem. Great job reaching the end of this walkthrough. In summary, we tackled the problem by analyzing constraints and solving it with an efficient O(n) approach. Remember to practice similar string manipulation problems to strengthen your understanding. Thank you for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!